Our next topic is conservation of energy. And the key idea here is that the energy in a system, and you get to define the system from a small scale, maybe something inside of a box in your room, or maybe the room itself, or maybe the building that you're in, everything in it, or maybe your town, or in this case, as you see in the diagram, perhaps it's a generating system for electricity that goes out over a great distance. Or perhaps in the biggest sense, it's the Earth, or even a larger sense, our solar system, or a larger sense, our universe. Any of those would be a system, but if we draw a box around any of those systems, the total energy inside always remains the same. But it can transform from one form to another over time. So let's take a look at our conclusions from our last exercise that we did. We were bringing a box of paper across the room, dragging it across the room. We dragged it around the room, and we carried it up to Mr. Conlon's room. And we discovered that when we were dragging it across the front of the room versus going around the perimeter of the room, the work done by friction and the work done by you had some problems with it. The big issue we saw is that if we changed the path and we tripled the path, it turns out the amount of work done by you and by friction was tripled. We noted also that the work done by friction is always going to be less than zero. You should be able to explain that. The work done by a normal force will always be zero, and you should be able to explain that. And the work done by you may be positive or it may be negative. If you are, for example, in this case, if you are lifting the box, it turns out your work is positive, and if you are lowering the box, it turns out the work is negative. And you could think of some other situations as well. One thing you might want to think about is, what about the work? And the key idea that we discovered here is that the work done by these types of forces is not reversible. It cannot be recovered easily. So once we slide that along the floor, we know that it loses energy to friction, and it has thermal energy, thermal heat that gets generated in the floor and in the box. But we can't pull the box backwards and suck up all that energy and cool things back down. It's very difficult to recover that lost energy that we've transferred into the floor and into the box in terms of thermal energy. Keep in mind that there are other types of what we call dissipative energies. Thermal energy is one, but sound, light, vibrations, etc. are all dissipative energy forms. And if you are losing energy to those, it's very difficult to try to contain those and recapture the energy from those. On the other hand, work done by gravity and by springs was quite a bit different. Well, first of all, let's go back. When we lifted the box and our change in our height, our displacement vector is positive, we found that the work that we did was negative because gravity is pointing downward, the force due to gravity, and our displacement is upward. And we found that potential energy is stored. So the potential energy we're storing is the opposite sign of the work that we were doing. Similarly, if we were to lower the box, the opposite would occur. And the key idea here is that the path didn't matter. We chose three different paths. One was going up the stairs to Mr. Conlon's room. One was going over to the elevator. We went down by mistake, then back up, and then over to Mr. Conlon's room. And the third case, we moved over to Mr. Barnum's room, put it out the window, hauled it up using a pulley, and then into Mr. Conlon's room. Didn't matter. All three cases were the same. So this just shows you that I could put it up a twisty staircase or a straight staircase. In the twisty staircase, I'd have more lateral displacement, but the vertical displacement is all that matters. Another key concept here is that when I actually raise this height and add energy, potential energy to this object, it's pretty easy to get the energy back. All I can do is let it go and it'll turn into kinetic energy, and perhaps I can do some interesting work with that. And we had a brainstorming session in class what we could do with that work. So when you see a force that occurs where the path doesn't matter in terms of the energy or the work that's done, and that you have an easily recoverable system if you move something backwards, we call that a conservative force, as opposed to a non-conservative force that we saw with friction or the work that you did. And as it turns out, anytime you have a conservative force, the potential energy function that you have can be derived by looking at the work done. So calculate the work done, and we can change that to potential energy. Just remember that the potential energy has the opposite sign of work. So let's take a look at the gravitational potential energy, and let's derive this formula. So first of all, we're going to move our weight up these stairs. And let's take two paths. One's a traditional path. We'll walk it up the stairs. The other path is we'll go through a crazy path here. And here's our crazy path. All right. Now, as you know, the work due to gravity, as we found when we did the box, brought the box up to Mr. Conlon, didn't depend on the path, but it only depended on the displacement. And we could draw a displacement vector straight from the object from its initial to its ending point. And we can calculate the work using our vector dot product of force of gravity dotted with the displacement vector. So these other two paths are junk. We don't need them. All we need is that displacement vector. Those other paths are distractions to you. So there's our force due to gravity, and that's what we'll be taking the dot product with. But let's actually look how we break this dot product down. First of all, notice that if we're taking this as our angle, it turns out if we look at the supplement to this angle, which is over here, which is 180 degrees minus our theta, it turns out that cosine of theta for this obtuse angle that we have is going to be negative, because we'll be in quadrant. If we're turning this sideways and look at it as an x-axis, would be greater than 90 degrees. We'll get a negative value. And it turns out if we use this angle instead, 180 minus theta, that will give us the same value, and we'll just have the negative in front of it. Because what I want to do is I want to show you, I want to use this angle because I want to break down these two side lengths here using this angle over here. And so our cosine of theta, we can substitute a 180 minus theta for, and it'll add a negative sign for us. And the negative sign is coming about because when we take the dot product with these two, this red component and our gravity are going to have an opposite sign, so we get our negative sign. And so our value of d cosine of theta is actually equal to our height difference. So in our dot product that we're doing for work, it turns out that we're actually picking out a height difference for our gravitational work. So our work done by gravity then is Fg times d cosine of theta, and d cosine of theta is just delta h, so it equals negative mg times our height difference h1 minus h0. That's the work done by gravity. Now remember, as we increase our height, the work done by gravity is negative, and the change in energy stored is positive, which just tells us that for our gravity or any other conservative function, the work done is negative, but the potential energy for that same work being done is positive for that situation, or vice versa. And so our potential energy function due to gravity equals the negative of our work function, which equals, if we take a look at this negative sign, will just disappear. So we have mass times gravity times our final height minus our initial height to get our change in our potential energy. We had a similar situation for springs and elastic potential energy. And if you go back to your lab, you can refresh your memory on this. But what we did is we looked at the area under the curve and found that was the work done by the spring. As we push the spring, remember that our pushing force was opposite the displacement, whether we're actually stretching a spring that's a tension spring or compressing a spring that's a compression spring. And that's why we have a negative slope on this. And we found that the slope of this curve is f equals minus kx, and we took the area multiplied by delta x and took half because it's a triangle, and we got the work done by a spring is negative 1/2 kx squared. And remember, just like gravity, the potential energy due to the spring, we're storing energy when we compress it or stretch it. And so we are increasing the energy even though we see a negative work done. And in the same sense that we had before with gravity, the potential energy for the spring is opposite the sign of the work. And so we have our work done by the spring equals negative of our potential energy stored in the spring. And just remember, we use U instead of PE for some textbooks. Let's take these ideas and revisit the work kinetic energy theorem. And what we're going to do is I'm going to step you through a little derivation starting with this formula. We're going to do some substitutions and see what comes out at the end. So let's start with the work kinetic energy theorem. And let's just suppose we have some general problem where we have some work done by you, by friction, by gravity, and let's say there's a spring in there as well doing something. So the net work that we need to put into our work kinetic energy theorem will be comprised of all four of those components. So let's go ahead and we'll substitute our work net into this, plug in. We know that for work done by gravity and work done by the spring, we can substitute in negative potential energy to gravity, negative potential energy for the spring. So that's that substitution. And I will substitute what we solved those for on the previous 2 pages. And what we have is, here's our potential energy formula we solved from before, and here's our spring formula. And what I'll do next is I'm going to distribute these negatives in to here and to here and to here, the first and second terms. And we'll add a negative to the first term, and we'll cancel the second negative in both cases. And then I'm going to rearrange things a little bit. I'm going to take everything that has a final value, move it to the right side of the equation. I'm going to take everything that has an initial value, which is this term, this term, this term, and move it to the left side of the equation. These two sources of work, which is the work done by you and the work done by friction, I'm going to group those together because those are all forms of non-conservative forces that are being applied to the system. And I'll just call that work non-conservative as a general term. So after we distribute our negatives and rearrange a bit, you'll see what we have is left here. We've got, here's our initial potential energy due to gravity. Here's the initial energy we have stored in the spring. Here's our initial kinetic energy due to motion, 1/2 mv squared. And here are our 2 components with us and friction, and I'll replace that in a moment with work non-conservative. And on the right side, we have our final values for the 3 forms of energy. So just replacing these with our variables, potential energy and kinetic energy. Here's work non-conservative. We have this equation left, and this is a key equation. There's a main idea in Chapter 5, and this is it, that the total energy in a system is constant, although it may change form from one type of energy to another over time. And you notice up top here, we have the total energy at time 0 equals the total energy at time 1. And you could expand this to say it's the same as at time 2, time 3, or any other time in the future. And what we have is at time 1, we have some sort of mix of different types of energies and potentially some non-conservative work being done. And later, some later time, that work could be redistributed amongst other forms of energy. And just remember, some books use a U for potential energy rather than a PE. So the left side of the equation represents the total energy system at some point of time, and the right side is the total energy at some other point of time, but perhaps those energies have different levels and they've been changed from one form to the other through the use of work. And just keep in mind that the non-conservative energy shows up in the left side of the equation based on our derivation. And those are things like us pushing, friction, rocket motors, things that are non-conservative, things that are dissipative forces. Also keep in mind that Chapter 5 is limited to mechanical energies, which is really looking at gravity and springs and forces and friction, external forces and friction. But don't forget that all forms of energy are conserved. We could have chemical energy, biological energy, and we could work these into the equations. There'd be a little bit more work to do, but it's doable. So let's revisit a problem we did in the past. We had Sophia, who weighs 44 pounds, which is 20 kilograms, sleds down a hill and reaches a level area at a speed of 10 meters per second. I did drop this speed a little bit for 2 reasons. Number one, if it was at 20 meters per second, the snow would have been really sticky, and we would not have been able to get down the hill in a second problem that I'm going to show you. And secondly, 45 miles per hour is too fast for a 6-year-old. So when she reaches the level area, she slides for 30 meters and comes to a stop. And from that, we can determine the coefficient of friction. In Chapter 4, we drew a free body diagram of Sophia sliding on the surface, and we made some assumptions about constant acceleration, and we worked out the problem using Newton's second law. Under the new method, we'll use conservation of energy. We'll still need a free body diagram because there's some work non-conservative done, so we'll have to look at the forces involved. And then we'll use the conservation of energy equation and plug in line by line. And don't forget, one of the first things we like to do when using energy equations, we like to see what terms zero out up front. So here's the free body diagram for the situation. Our force due to gravity is 200 newtons. Our normal force will be 200 newtons as well. And our force due to friction is going to be mu k Fn. This is our unknown mu k times 200 newtons. And I'm going to do this 2 ways. I'm going to start with a numerical solution, then I'll go through a general solution with you just to show you can do it either way. So we're going to use the conservation of energy method. So I'm going to write down, and I would ask that you do too, You can write down either conservation of energy or energy is conserved, and just show that the total energy at time 0 equals the total energy at time 1. And I'm just going to show, this is really general. I'm putting in all forms of mechanical energy that we're using. The potential energy of gravity at 0, and the potential energy of spring at time 0, and the kinetic energy at time 0, and the work non-conservative equals potential energy of gravity at time 1 plus the potential energy of springs at time 1 and the kinetic energy at time 1. Which ones of these are 0 or not applicable? Well, several are 0 and not applicable. If we define our height to be the ground level as 0, then all of our potential energies drop out. Our springs, we don't even have a spring, so we can knock those out. Our work non-conservative, we will use for that. We do have friction, so we're going to plug in an equation to calculate the work done by friction. So we'll use our dot product of the vectors to do that. And our kinetic energy at the end is 0. We have some initial kinetic energy from our initial speed of 10 meters per second, but that slows down to a stop, so that drops out. So most of the things drop out of this, and we're left with a very simple relationship that looks like this. And if you did this using the work kinetic energy theorem, you'd find out it works out the same way. So I'm substituting in for the initial kinetic energy and the work due to friction, and let me throw in some numbers here. And the reason, one of the things I like to do with the numbers here, it allows me to actually see the total energy of the system at different points along the way. And it turns out that I have 1,000 joules of energy initially, and that 1,000 joules of energy is going to, over this distance, it will be consumed by the work non-conservative, and I'll end up with 0 joules of energy in the end. That's how I read this last line. And if you just plug in the numbers as I've done, you find out, and if you solve for mu k, that mu k equals 1/6. Let's look at a general solution for the same problem. First lines are the same, and we were here before, and our cosine of theta is going to be -1. I'll go ahead and use a -1 there. You can let me use one number, and that just changes sign to a negative. Our work done by friction is negative. I can now solve this equation for mu k, and I end up with this result. I can plug in numbers, and I get 1/6. Same answer. Remember, mu is unitless because we're dividing a force by a force, and the units cancel. Now, let's turn the problem around a little bit. Suppose the hill that Sophia was on makes an angle 30 degrees with the ground. How high up on the hill did she start when she started the sledding to get to 10 meters per second down at the bottom? I've worked out some numbers here, and now we've got a rotated axis because we do have gravity acting down and this box is sliding. We still have a 200 Newton gravitational force, and I've broken that out over here. This angle is 30 degrees, and so this angle is the same 30-degree angle here, so we can work out FGY and FGX to get our normal force of 173 newtons is going to be Fn, and our force going down the hill is 100 newtons. And we do have a frictional force acting against us. And it turns out our frictional force, once I corrected these numbers, is 28.9 newtons. And now we have enough force going down the hill to overcome friction and slide. When I had a 20 meters per second ending velocity before, it actually made our mu k very high, and we would have been stuck to the hill. Once again, plug into my equations, and we were here before, and the key here on this problem is, here's my height that I want for energy, so that's the height of the hill, and I've got this displacement going down the hill, and it turns out they're related through theta. So I can either solve for the height in terms of d sine theta, or I can solve for d in terms of h0 divided by sine of theta. They're equivalent. And what you see down here is I'm going to plug in numbers, and it turns out you get a height of 7.03 meters. A general solution looks very similar, and you get a cotangent function in here, sort of like our object sliding down a ramp when we lifted it in our friction lab. So try out these methods, and the key is to use this total energy equation and step by step knock things out, plug things in, and see where you come to the end.